guest on to talk about Amazon Neptune Serverless, and that is
Welcome.
Kelvin. Now, why don't you introduce yourself, Kelvin?
Yeah, well, first of all, thanks for having us, myself and the Neptune team on the show. It's always great to come show people a few fun things with graphs. I'm Kelvin. I'm a senior principal architect on the Neptune service team, just a small part of a great team, and looking forward to showing you some cool new Neptune stuff we've got to talk about.
Sweet. Yeah, I know there's actually quite a bit of anticipation around this. We already got several questions in the chat about when Neptune was coming. So let's get right into it. Can you tell us a little bit about your launch today, Kelvin?
Yeah, happy to do that. And also, as we go through this, I know for some of our viewers, graph is still kind of a new thing. So we'll show you some little pictures and talk a bit about graph as we go as well. But traditionally, when you provision a Neptune cluster, you go to the AWS console and you create a cluster, which is basically the storage, which is across multiple availability zones. And then you attach instances to it, which do the compute. So typically, we would attach, say, a 2x large R5 cluster instance, EC2 type as our Neptune instance, and we would keep that there, and you can have one writer and up to 15 read replicas in a cluster as you need them. But you have to kind of know ahead of time or work out by practicing what kind of instance sizes you need, and you pay for the instances that you provision. So what we've launched just this week is the ability, when you provision a cluster, is to have the option that you don't use these fixed size instances, but you use serverless ones. And as the workload that the customer is running increases, Neptune keeps track of the CPU, the memory, the IO that the queries need, and will scale up that instance in response to that. And then we'll also scale it back down again as the workload subsides. So if customers have a workload that is bursty, doesn't have sort of continually high peaks, so it maybe goes up and down, they're not quite sure when it will be bursty. Maybe they're doing development and testing, or maybe like the demo we're going to do today, we can pretend I'm a data scientist that works 9 to 5 and I don't use my cluster at night. The cluster will scale back down to the low end number that you configure for your serverless scaling, and you only pay for the compute that you're using. So we talk about Neptune capacity units, and we'll look at this when we go through the whole demo. And that way, not only is this giving you an easier way to configure and manage the way your cluster scales, it's also a way where, as we're always focused on, helping our customers save money. So they're only actually using serverless, paying for the compute they're using. And if they have a bursty workload, they don't have to over provision to anticipate what might be coming next. So in a nutshell, that's Amazon Neptune Serverless.
Well, that makes a lot of sense. For those who maybe maybe they're used to using a relational database, can you tell us a little bit about what makes graph databases special? Like what
absolutely
solve with this graph database?
And why don't we do that sort of talk and demo at the same time? I think that'd be a great way.
I like that. Yeah.
So I'm going to go back in a little bit, and we'll show everyone how we created the cluster. But like just before the show, I created a serverless Neptune cluster, and I'm using a Jupyter notebook here. We allow and make it easy for customers to provision a Jupyter notebook that comes preloaded with all kinds of special commands for working with Neptune. So a developer, a data scientist, anyone who wants to work with the cluster, this is one of the ways you can do it. And we'll show a little bit later how you can provision that. But we just have to tell our notebook that, hey, there's the cluster we want to connect to. We can just check out, are you alive and well? We can see that the cluster is healthy. So we're good to go. As we go through this, Nathan, we'll show 2 or 3 different examples, and Neptune supports 3 different graph query languages. One is called Gremlin, one is called OpenCipher, and one is called Sparkle. And Neptune supports 2 different graph data formats that you can store in Neptune. So a lot of flexibility. None of those things are proprietary. They're all based on open source and open standards. And one of the nice things to your question with a graph is there is no schema ahead of time that you have to design and build. We can just create our cluster and start putting data into it. So despite the flag behind me and my very obvious Texas accent, I actually do live in Texas. So we're going to create a little graph to start with where in a graph, you really only have 3 things. You have nodes, sometimes we call those vertices. You have the relationships, which we call the edges sometimes. And you can also have properties, which some people think of as being sort of just extra bits of description that you can use to describe, like my node might have my age in it as a property, something like that. And you
That's
can think
interesting because I'm already seeing a difference there. I'm used to, like, if I was doing a relational database, I have to set up a bunch of columns. I would set up like people, and then it would be column for like what's my state, column for what's the person's name, column for what company they work
that's
at.
right. Yeah, and I think when people come to a graph database from a relational background, that's one of the things that you have to get your head around a bit, is that you don't define a schema ahead of time that has rows and tables and columns, but you can sort of think of a vertex with properties as a row in a table, if you like. So we're going to create 3 nodes here. We're going to create one for Texas, one for me, and one for AWS. And then we're going to create a couple of edges that associate me with where I work and associate me with where I live. So if we run that, hopefully it'll come back in a second. There we go. My network is a little slow. I'm a little paranoid today. We've been having bad weather down here, so keep your fingers crossed. So we've now, into the empty graph, added that little bit of structure. And then right now we're using the Open Cipher query language. And you notice, for people coming from a SQL background, maybe moving to graph, this looks a little familiar. You've got things like where clauses here. So hopefully people can sort of read how this works. And what we're basically going to do is we're going to now search in that data we just created for a match for a person who lives in the state and works at a company, and that person has my name. So let's run that. And so far, okay, we got some data back. We could look at it as JSON, but it's not particularly exciting. But one of the things I really like about graphs is they kind of model the way we think in the real world about our relationships. So, we all work at AWS. We all have friends. We all maybe have social networks that we're on. And we sort of think, even though we may not realize it, in terms of graphs when we work with our everyday lives. So now we can sort of see what I just created as a picture, which is where I think the power of graph really starts to come home. So as well as being able to get your data back in a text form, we can actually visualize it. We can move it around. We can play with it. And you can start to explore more and more the data in your graph visually. So in a nutshell, that is a graph database right there on the screen. We've got nodes. We've got relationships. We didn't add any properties, but we could. We could, for example, have put my age in here as a property, and then it would show up. When we click on it and look at the details, we would see my age, but we didn't put it in there. But in a nutshell, to your question, that's really how graphs work. And if you're from the relational world, you can sort of think a little bit of nodes, a bit like tables or rows in tables. You can think of edges a little bit like joins between tables. But the nice thing about a graph is it's all pre-computed, and the graph query languages can easily then answer questions like, where does Kelvin work, or where does Kelvin live? Or we could add people and say, who does Kelvin know?
And I can already see how fascinating this is. I essentially, rather than having one table, I can now start any of these different entities. Like I can start from Texas and then say, give me a list of all the people who live in Texas.
Absolutely.
That I know of, or give me a list of all the people who work at AWS that I know of. And so I can start exploring from anywhere through these edges inside the graph. But I imagine that's probably pretty computationally complex, right?
And I think that's where graph query languages and graph engines like Neptune come into their own, because you could imagine in a relational system or DynamoDB tables, you could very easily build one-hop representations of sort of Kelvin to Texas, Kelvin to AWS. But when we start to explore deeper and say, who else works at AWS, what department are they in, who else do they know, and we're maybe 6 or 7 levels deep into that search, that's quite hard.
So if I was to do that as a DynamoDB query, I would probably be scanning through and fetching out, maybe potentially thousands and thousands of items out of that DynamoDB table. That will become a very expensive query.
and quite hard to write too, because SQL and Dynamo type solutions are great for many of the things they do, but they weren't designed for this kind of very deeply recursive searching through lots of relationships. And that's where a graph database comes into its own, and that's what it's designed for, is that computation of those interesting sort of hops around the graph looking for who knows who or who's connected to what.
That's amazing. So how does Neptune Serverless apply to this? Because you mentioned that it will help you to save money on there. How does Neptune Serverless apply to this? What you're showing here, this very computationally fascinating way to store the data.
Do a couple of things. And by the way, just in passing, I put this in. Anyone who's a Cypher guru watching us will be saying, but he could have done all of that in one query, and it's true. I could have created it and returned it all at once, but I acknowledge that there are other ways to do it. So to answer your question, I'm just going to kick one thing off, Nathan, then we'll talk about that. So there's several ways to load data into Neptune. One way is you just write a query like we just saw. We also have a bulk loader that can load large amounts of data from S3 buckets into Neptune. But in these notebooks, we also have a little thing that we call seed, which comes with some sample data sets. And there are sample notebooks as well that go along with these that help people learn how to write queries. I'm going to kick off loading the airport data set, and it'll take a few seconds for it to load. So while it's doing that, if I hop back over here to answer your question, and let's go look at the Create Database tab, you can see here that traditionally, as in last week, before we announced serverless, you would have only seen provisioned instance types here. But now we have the option to pick a serverless one. And by provisioned, I mean you pick a fixed size instance like a 2x large or 8x large, whatever you need, and however many read replicas you need. Whereas with serverless, we can be a little more selective. Notice that the Neptune engine version actually changed when I picked serverless, because this is a new engine version that comes along in support of serverless. And then I already created the cluster, but we can pretend we're doing it again. And so we'll call it AWS on air. But where it gets interesting is this next box where you see we can set our capacity settings. Right now in Neptune, we've allowed the minimum to go as low as 2.5. We found that in our testing to give customers good availability, even at the low end, 2.5 is a great place to start. And the maximum you can scale up to with these NCUs, or Neptune capacity units, is 128. And you can choose a start and end value that's not the default. You may, for example, only ever want your cluster to go up to 64 units because you kind of know where your peak is, but not quite, but you don't want to allow it to go beyond that. And Neptune will scale up based on what your starting value is. And if you have a bigger starting value, it will actually scale up a little quicker each time. But based on where it currently is, it will scale up intelligently. And Neptune is always looking at how much CPU your queries are using, how much memory your queries need, and how much I/O your queries are using. And we'll try to scale up appropriately. And so as that load that's going on in the background now is happening, our serverless instance will have noticed, oh, Kelvin's given us a bunch of work to do. We need to scale up. So we'll look at CloudWatch a bit later and we'll see that it's actually been responding to that. And once those workloads die down, let's say my load runs for a minute and it's over, our compute units will start to scale back down again. So I only paid for the compute units I needed during that time. And it's about 16 cents per NCU hour, and we prorate it to the second that you're billed for these capacity units. So it's a great way for customers who have bursty workloads, or someone like me pretending to be a data scientist. I'm just sitting here working 9 to 5, to actually only pay for the compute I'm using rather than provisioning an EC2 instance, say an 8XL, because I'm trying to guess what my maximum peak might be. And then I'd be paying for that capacity, but maybe never using it.
That makes a lot of sense. This immediately reminds me of a past startup I was working on, feature to make friend recommendations. So we wanted to look for like friends of friends that had certain relationships that might be good recommendations, right? But we didn't regenerate those friend recommendations, constantly. It was more like once a day we would regenerate it in the background and then feed out those recommendations to everyone. So this instantly makes me think, okay, well, I could have that scale down to almost zero 99% of the time, and then scale it up once per day automatically to regenerate those friend recommendations. That's fascinating.
Your example is spot on, Nathan, too. I think that's exactly the kind of use case where serverless will help our customers. It will allow them not to have to provision bigger instances for those bursty times or try to intelligently guess when they need to maybe have a CloudWatch metric trigger and then go stand up another instance. The instances will just scale themselves up as needed, like for your example with your once a day calculation. Then they'll scale right back down again to the minimum.
Wow.
Super useful.
So if we hop back over to our other tab, the load we can see is done. And I included a Gremlin query here, and I'm hopping around a little bit between the query languages just to show the viewers the kind of different languages we support. So very quickly, The data I just loaded is an air routes data set. It's one of my passions. It's a data set I've loved for a long time. And it models the world airline network. So we've got airports and we've got routes and we've got information about the airports. And we can do all kinds of fun queries about where can I fly to from A, and how many hops is it to get from A to B, and that kind of thing. So if we just run very quickly this Gremlin query, we can see we got lots of data back, which is interesting. But again, the picture is much more interesting. And you can see what we've done in the query is we've said find 15 places you can fly to nonstop from the London City Airport. And here we've got the names of the airports. We've also got the distances of the routes. And if we were to go click on Venice, we can even see all the properties we've got associated with Venice, hence the term property graph, because these extra properties or attributes show us things like the elevation of the airport, which in the case of Venice is not very high. But so that's kind of, the next level where we're starting to explore a bit more. And then I used an open cipher query to get a little more complicated, which is I'm going to go 3 hops. That the times 3 means I want to go 3 hops starting from London City and find me 6 routes that are 3 hops from there. So we're going to run that query now. And again, we get the text form back, which if you're writing a program, you need that. You need the text. But for our human user, the picture is much more interesting. And we can see that we got London City back. I'm going to just drag it around a little bit so you can see the picture a bit better. So we came from London City and then we went to a few other places. And we have settings in here that you can actually control the way this looks a bit better. But hopefully you can start to see here, this is a bit more complicated because we've gone from London City, we've gone to Frankfurt, which we then went to FCO, which I happen to know is Rome. So hopefully that shows where it starts to get interesting, because the query we wrote is really a one-line query, right? We just said, find this pattern. And by the way, I want the start to be London City. Imagine if we were, and this is not to knock SQL, because SQL does millions of things really well, but imagine if you were trying to model this and write the SQL queries to do this, they get quite complicated. And so this is really, in a nutshell, the value of graph, which is where we're able to do these quite complicated questions really easily because the query language is designed for it.
And I love how you're just switching between query languages, like every cell. Just be like, oh, in the same data set, you can just do it in like 1 line or like 3 lines different. This is super cool. I'm still pretty new to graph databases, and yeah, I'm kind of harkening back to when I learned SQL back in undergrad and just struggling with the sorts of queries that you'd have to write for relatively simple things like this. So yeah, it's really fantastic.
Well, I think also a lot of application developers these days, they do the joins in the application side code as well. So in that case, a lot of these types of queries involve reading data into the process memory, and then you have to send out a bunch more queries to fetch even more data in. And so then you end up with a lot of latency, whereas this can all happen on the server side inside of those NCUs that we talked about earlier.
That's right, and we'll check out CloudWatch in a minute, and you can see it's responding really well. But behind the scenes, Neptune's been scaling up, as needed to meet the demands that we've been putting on it. So the load we did was actually quite a big load, and we'll see in a minute it will have scaled up to meet that.
Now, does this also have benefit for sort of like an always-on workload? Like, let's say I wanted to do like some type of real-time graph processing as well.
I think it depends very much on the amount of capacity that real-time workload has. So, for example, if you know that your real-time workload would never need more than the compute units that you get from 128, or Neptune capacity units rather, and maybe you know that it always needs, say, at least 32 gigabytes of memory, and a Neptune capacity unit scales up in 2 gigabytes per unit. So let's say you knew you needed at least 32 gigabytes of memory, but you might need to go higher. We could configure our minimum to be 16 capacity units. We could leave our high end at 128. And as long as we knew that our workload would fit within that and would still potentially have less stressful periods when it wouldn't need to always be up at the 128 level, serverless would still be a good option. There will be cases where if you wanted to go really large into some of the really bigger instance types that we support that go even bigger than the 128 that you can get to with serverless, you would still consider using those instances if you had something very specific that just needed really substantial amounts of memory beyond the maximum that you can get. right now from serverless. But for sure, we anticipate all kinds of workloads, including the one you're describing, being a good fit for serverless, unless you need, the absolutely maximum amounts of memory that you get from some of the really big provisioned instance types.
Yeah, that makes sense. And I can also imagine perhaps if there was something that was like spiky, like it was event based, like a bunch of people suddenly sign up at once or try to use an endpoint at once. It feels like this will be able to adjust to that more quickly than I would going into the console, switching an EC2 instance
That's
out
right.
to scale it up.
And that's essentially what you would have to do. So let's say you had 3 read replicas in a cluster and they were all provisioned, and say they were all 2XLs, and then you suddenly realize it's the holiday period and you're doing something to do with selling. You would have to go in there and replace all of those based on what you think your peak's going to need for, say, the next 3 weeks. Whereas if you're using serverless instances, you could just set that Neptune capacity unit maximum to a high number, still have 3 read replicas, they'd just be serverless ones, and they would automatically notice the increase in demand, and they would start to scale themselves up. And so you wouldn't have to do exactly what you described there and go essentially be replacing those instances, using the console, standing up a new one. And it takes a bit of time to do that. So this is a much more responsive and adaptive way of handling those kind of workloads.
Well, this looks very exciting. I can't wait to build with it myself and see what folks are able to build with it. Is there anything else you want to tell viewers about where to go to get this started at, where they can get this notebook from?
Yeah, let's just a couple of quick things I just wanted to show, because I think one thing that is important is, people watching this are probably going, prove to me it's real.
Oh, yeah.
So, we'll refresh this in a minute and we'll see the latest. But when I was prepping the demo for today, one of the things I did was just load all the things to make sure they worked. And you can see that the cluster began at 2.5. So we can see our serverless database capacity there is at 2.5. The NCU utilization is just a percentage of the maximum that we're currently using. So we know that 2.5 is 1.9% of our 128. That's all that means. And you can also see that the CPU wasn't doing very much there. So our cluster was pretty much idle at that point. Then I started doing my testing. I loaded some data. All kinds of things started happening. And you'll notice that we scaled up to 23. And that's what it needed to do the prepping I was doing. But then once I stopped and I was sitting here waiting to go live with you all, it just scaled back down. And again, it went back down to 2.5. And if we just refresh the view now, or maybe I'll make the granularity just a little bit, make the granularity a bit less so we can see it more clearly. I'm going to set this to be 5 seconds. I'm going to set this to be in the last hour. So you'll see that while we've been on air, that little cluster was at 2.5 when we started. Then we loaded the data. We ran those early queries. We ran some tests. And now we've stopped. You can see it's already on its way back down again. And you'll notice it doesn't immediately drop back down because it anticipates you might have more coming. So it tries to intelligently drop itself back down so that if you suddenly came along with another big query, it wouldn't have to go all the way back up again. It could just pick up from where it is. So hopefully that kind of conveys the way, what's been going on in the background anyway, while we've been loading the data and doing the tests.
And I like the fact that it looks like it's really responsive. It looks like it scales up really quickly. So it's not like I send a query and then I have to wait like a couple minutes while it gradually scales up.
That's right. And it's intelligent in that it, depending on what the starting value is, so we started at 2.5, it will initially start to scale up based on that. But if it notices it's getting more and more work, it will start to scale up faster as well. So it tries to be intelligent about how quickly to scale up and how much to scale up.
Cool.
Very cool.
And just to answer your question on notebooks, when you launch a Neptune cluster, I guess just to show everybody exactly how that works, when you launch a Neptune cluster, it's going to go back to my databases view. You have the option to create a notebook at the time, or you can come over to the notebooks tab and see your notebooks and create a notebook. Those notebooks are hosted by SageMaker. And when you come over to those notebooks, you'll see all these 01 through 06 notebooks are preloaded for you. So for example, if you wanted to go and play around with the AirRoots data set, we've got Gremlin, OpenCipher, and Sparkle versions of it right there. So all the things I'm showing you here are in those sample notebooks. So the data is all part of the notebook experience as well. So anybody
And,
wants
and
to
does it create it like automatically with the right IAM role to like connect to the Neptune and talk to it?
It does. So if you provision the notebooks from the Neptune, AWS console, it will take into account making sure the roles are correct and everything else is there. So the minute you go to your notebook, as long as you've got the AWS IAM permissions to access the cluster, you can just start doing what we did in our little demo, and you can go at it straight away.
That seems like a huge boon for data scientists, because the last thing you want is for a data scientist to accidentally open up the database to the entire world, getting the configuration messed up. So this seems like a very like all batteries are included product. It's ready to go. It's ready to test out. I can't wait to see it in action.
And I'd be remiss if I didn't mention, Nathan, that we open source the whole Jupyter Notebook experience. It's in GitHub. It's called Graph-Notebook is the name of the project. So people can also self-host this on their laptops if they want to. They don't have to have us host it for them. If we host it, we just take care of all the management of it. But if they want to just run it on their laptops and use it on an airplane, they can do that as well.
Awesome. Thanks so much for showing us this.
Yeah, thanks so much, Kevin.
Yeah, thanks for having us. There's a lot more we could go into, but we've probably run out of time. So.
Yeah. I did have a banner I'll bring up here on stream. It says github.com/AWS samples, Amazon Neptune samples. So it looks like there's more GitHub open source content to look at if you want to go play with this today and get started.
Yeah, and if anybody searches in their browser for Amazon Neptune developer resources, it will find a page that's just chock full of links to samples and GitHub repos and reference architectures and all kinds of goodies.
Thank you very much for joining us on stream today, Kelvin, and look forward to chatting with you in the future. Next time we have another exciting Amazon Neptune.
Always happy to come talk about graphs. Thanks for having us.
Thank you.